Well, we have one more talk before lunch. I would like to introduce Mohammad Saffar from Arimo. Mohammad's going to talk to us about time series data and how we can learn effectively from time series data at scale. Over to you.
Hi, everybody. So I'm sorry I'm the odd one out. I'm using my own laptop. Sorry about that. And I'll try to keep it as short as possible. And as long as you guys promise not to ask hard questions, we are going to be good for the lunchtime. All right. Let's wait for the PowerPoint presentation to be set up. And a little bit about myself. I'm actually a software engineer. And the panel before my session is actually kind of put me at ease because I was feeling like, OK, I don't have a degree in math or statistics. What I'm going to do here? And so thanks, the panelists, for that. Awesome. Thank you so much. All right. This is the Grand Bazaar in Tehran. Who knows where that is? Awesome. This is my hometown. It's actually in Iran. And this is a very nostalgic picture for me. About 20 years ago, when I was actually a kid, I used to go there a lot. And I used to spend my time there and see people from different areas of the country visiting this bazaar and doing business and shopping. I used to remember that, I remember that my father used to really encourage me to go help my uncle, who also had a shop in this bazaar. It was actually pretty much close to the dome that I'm showing over here. And I used to go there and I used to just be in the shop and create a big mess. I wasn't really helping that much. And I was always constantly in his way, slowing him down. But I had a ton of fun while doing that. So I remember at some time, I asked my father, I told him, Dad, I can't really help my uncle anymore. I mean, I'm just slowing him down. What is the point of me going there and just making things even worse for him? And my father told me, not in English, of course, but I'm going to translate it for you guys. He told me that, son, this is for your own good. When you grow up, no matter what your profession will be in the future, you're going to end up interacting with a lot of people, and you're going to see different personality traits. So the more you do business with people right now, the smarter you'll get in the future. And I didn't quite understand what he was saying until so much later. And fast forward 20 years, here I am. I think I know what he was saying back then. Interacting with people from different walks of life is a very, very golden experience in my mind. People like salesmen, recruiters, or business owners, they should be really good at this because they are interacting with people on a daily basis, and they should have a deep understanding of the other side of the conversation. And the experience, I think, in my mind, is the key. So the more you interact with people, the better you get. And you develop a kind of like a gut feeling of what the other person is really want to do. Honestly, I have to confess, I'm not really good at this because I don't really interact with a lot of people in my job. But being a deep learning software engineer, we always tend to create smart systems to do the things that we are not really good at ourselves. And I'm no exception to that. And my today's talk is actually about that. Sorry, I'm not checking Pokemon Go. It's going to control that. So my today's talk is actually going to be about that. I'm going to talk about a deep learning solution that we developed to analyze and understand human behaviors as some people can do. Of course, I was not one of those people. My name is Mohammad Saffar, and I'm a deep learning software engineer at Arimo. So we talked about behaviors, and if you ask me what is a behavior, the honest answer is that I really don't know. But engineers normally have a solution to whatever you give them, even if they don't understand the problem. And this is what I did, actually. We try to see behaviors as basically a sequence of activities over time that a person is doing. And that is basically a time series of actions that is being captured by a system. So take clickstream data, for example. A customer is interacting with the business. Whatever they are doing, what action they are choosing, and the timestamps, these are all being recorded as a clickstream. And we normally see that as a proxy to understand the behavior of that customer. And my today's talk is basically about that. I'll focus on that specific use case. But I just want to briefly talk about other sources of time series data. We have seen a wide range of different data sources like genomics data, IoT and sensors. They're definitely sources of time series, all the way to financial transaction and stock market movements. And I just want to clarify something. I mean, when we are talking about time series, what I really mean is really sequential data. A good example of that is going to be language. We have words, and the ordering of the words in a sentence contribute as much as individual words to the meaning. So it's really more than being related to time. It's all about sequential. And as we can see, we can do a lot of interesting things with these data sets that we have. I'll talk about the customer segmentation use case today in more detail, and I'll talk about how fundamentally different we can look at this problem when we really consider time series. And other similar approaches, they actually failed at capturing the essence of behaviors. I'm going to talk about that as well. But other use cases like marketing, one-on-one marketing, portfolio diversification, predictive maintenance, they are all can take advantage of deep learning models and the way that the deep learning models can naturally process time series data. All right, I think up to now, you guys have guessed that I'm a big fan of deep learning. I just want to briefly talk about my personal experience and how I got exposed to this interesting technology. So when I was in graduate school, I was researching in computer vision. And around 2012, so I was following the advancement in the ImageNet challenge. That was a big thing in computer vision. About 2012, we saw convolutional neural networks making a huge improvement over traditional computer vision approaches. And back then, the state of the art in computer vision were basically systems that were using a large set of features, handmade features designed to detect key points. What I'm showing over here is basically a SIFT key descriptor, which is basically a smart way to represent key points in an image in a scale and rotation invariant manner, but is handmade. So it's kind of like an intelligent design. Somebody decided to do this computation to capture that key point. And we all know the history of perceptrons, and the early promising results. The perceptrons also later got shattered by finding out that these models are really failing at basic tasks if you don't give them very, very smart features. So overall, we can see the learning part is actually the easier part. Whatever we feed into the model and defining those features becomes the hardest problem. So can we do better? Can we create a system to actually learn these features? So contrasting intelligent design with something like evolution maybe, can we have something that gets better over time? And in my mind, basically deep learning is all about that. And let me just, sorry. Okay, let me just use this, it's failing. So deep learning is really all about that. And we can see how a very, very big neural network, interconnected layers, can learn a hierarchical structure of features and for that specific task they're designed for. I have an example over here. We can see how convolutional neural networks can learn different features, and starting from very simple ones like edges or corners all the way to actual complete faces. The other example that I'm showing is my favorite model in deep learning. It's called Word2Vec. We can see how a language model just trained on raw data can put words into very compressed numerical vectors. We call them embeddings. And we can see how similar words end up actually closer together, or grouped together in the embedding space. So with that history about deep learning, I want to talk about time series data. And can we actually use the same kind of idea to process time series? So I'll talk about the previous approaches. Normally, we have the raw data set in this long format. We have all the observations as separate rows in a long data set. They have the timestamp and other features capturing what happens at a specific time. What people normally do is they get this long data set and apply a grouping operation on it, plus some aggregation function to create a collapsed feature vector that represents individual entities. And then this collapsed feature vector goes into a predictive model, whatever that can be, to get the output of that model. So what happens over here is that while we are collapsing these rows with group by and aggregation functions, we are really throwing away valuable data. Imagine if I just selected maximum amount of money spent in the last 30 days, but it turns out that the minimum amount of money spent in the last 30 days is more important, and I just happen not to pick that myself. So we are really, again, going to the paradigm of hand-picking those features. Can we do better? And can we actually design systems to learn these relationships? And again, the answer is yes. And this is our approach, basically, to this problem. So starting again from that long data set, we create sequences out of that long data set that we have. We are not doing any aggregation. So we are not throwing away any data. And recurrent neural networks basically can naturally digest a sequence of features going into them. And what happens over here is that the model in its recurrent layers learn what to remember and what to forget. So it kind of learns to understand features. And as a side product of this approach, a sequence gets translated into one numerical vector. We call them embeddings, pretty much just like the word-to-vec model. And going back to the recurrent neural network idea that I talked about, this is basically a more detailed view of that component in our system that we developed. Again, inputs, we just treat it as a sequence. We are not really aggregating anything. That goes into recurrent layer. And as I talked before, that recurrent layer learns how to transfer a variable length sequence going into the model as the input and translates it into a fixed length compressed representation. We call them embedding. And what happens over here is that a sequence gets translated into a point in a high dimensional space. And we can see, again, deep learning models can go ahead and then use that embedding space to do predictive tasks, or we can directly use that embedding space to cluster entities together. And the idea here is that because the recurrent neural network actually sees all the input sequences, points that are closer together in the embedding space are points that are similarly behaving in terms of their time series data going in. And later, I'll actually show one example of how this approach works specifically for customer segmentation problem that I talked about. So, so the customer segmentation that we actually did, we captured clickstream data for about a span of 2 months, tracking about 1.5 million customers interacting with the business from different channels, cell phones, computers, and even physical interactions with the store. These were all captured in a data set, a clickstream data set, and we use actually Hadoop as a underlying data storage for a system. And we also employed Apache Spark to do ETL and translating this data or reshaping it from long format into sequential format. And then later we used distributed TensorFlow to actually scale up our model training phase and take advantage of basically a cluster of GPU systems to train a big model on a big data set. So our CEO, Christopher, actually has talked about the techniques that we use to do distributed deep learning. And I think if you guys are interested, I really recommend checking out his talk at the Spark Summit East, specifically about how we parallelized model training. So with that kind of overview, I just want to jump into a demo and quickly show you guys what I'm talking about. So if you don't mind, can we switch to that browser window? Or I can do it myself if it's okay. All right, perfect. So this is an initial experiment we did. So of course, images are very easy for us to judge. And before getting into a customer segmentation, we actually used the same technique that I talked about to find similar images of different products. And as we can see, this is actually a visualization of that embedding space that I talked about. And as we can see, the model was trained in an unsupervised fashion. We didn't really give labels of our products to the model, just raw pixels going in. And as we can see, the model learns how these similar product images are actually related to each other and puts them into specific groups. And we can clearly see how the embedding space learns to separate them out. So of course, there are some mistakes, but that's what we expect. So with this kind of view, we can see that the idea of grouping these entities into the embedding space actually works for images. Sorry. So let me quickly jump to our customer segmentation view that we developed. Again, this is the results. We actually are showing the embedding space. We did some dimensionality reduction techniques. This specific example is actually t-SNE. We just projected all the points into a two-dimensional plane. And every point over here is basically a customer. And we can see how clearly separated some of these groups are when we run our model. So I'm going to pick a couple of examples and actually talk about that in a little bit more detail. So I just selected one of these groups of customers. And we can see these are the salient features that we just used simple statistical measures to compute. We can see that this specific group, they are actually coming from a specific ad campaign. And the propensity to purchase is a lot higher. So this is a very good group. These are the customers who are profitable for that business, and they are buying fitness products, and they're interested in fitness, and the propensity to purchase is a lot higher. And that a specific ad campaign is actually working beautifully for them. I can choose another contrasting example. Let me just choose one other cluster. So we can see they are kind of similar. They are coming from the same ad campaign more often than the other groups. But the propensity to purchase for that group is actually a lot lower. So we can see the same ad campaign in our example works beautifully for a set of people and is not really working for a set of other groups. Just to show one final example, I'm going to pick another one. And we can see the third group, they are coming mostly from email campaigns. But again, the purchase is minus 14% less than the average that we expect. And they are mostly interested in arts and crafts. So something like that in the hands of a person like a marketing manager, we can see how powerful that can be for them to understand their customers and use this kind of data to put them in different groups, not by cross-sectional data. We don't care if they are male or female, what is their income rate. We just want to know how they are interacting with the business. And that's basically the fundamental change. And we can see how this tool can be useful for businesses like that. So I'm going to switch back to this. And basically, just one more slide and I'm done. Sorry, I'm just, okay. Perfect. So what else we are working on? Me and my other colleagues at Arimo, we are really focusing on what we call predictive behavioral intelligence, which at its core is just basically time series data and processing time series data based on recurrent neural network approaches. Other use cases we are working on, I can give you a couple of examples. We are looking at behavior-based demand prediction. This can be helpful for people to optimize their inventory. Automated incentive engine, because we can go ahead and look at individual customers, and we can really go ahead and compute when there is going to be a cart abandonment happening. Right at that time, they can ingest a offer to capture that customer. And finally, we are actually looking at techniques on time series data to detect anomalies and fraud. The idea is very simple. We actually go ahead and model the data and capture what is common in the patterns, and any deviations from that common pattern is actually detected as anomaly. So I think I'm done. Thanks very much for your time. If there's any questions, I'll be happy to answer.
Question already, right here. Sandy.
Thanks. How do you know when an embedding is doing a good job?
That's a good question. It depends on the problem, actually. For clustering, we all know it's a tricky problem. We can't really go ahead and compute the accuracy. What we normally do for clustering, we look at the similarities of points within a cluster and the distance between points in two different clusters. But again, that's a tricky problem, because if you go ahead and increase your cluster size, you're actually minimizing your inter-cluster diversity, which is a good measure. But it's basically a little bit tricky. What we did, we actually used some similarity measures like dynamic time warping to compute a similarity between different time series data and evaluated the clustering quality. But I didn't really show that over here because of the time. But that's what we did, actually, for that specific use case. Any other questions?
Back there.
How would you satisfy the requirement for, say, reason codes?
I couldn't hear you. I'm sorry. Can you repeat that?
Reason codes, if you needed to tell why your model is making a certain prediction.
That's a very good question, actually, and this is something that I think is still unsolvable for a lot of deep learning problems, deep learning models in production. And there is this trade-off between explainability and accuracy sometimes. And so if explaining the reason and if saying why a model decides something is really important, then maybe a deep learning model is not a good answer to that. Maybe a decision tree is better. But that's, again, a very objective discussion. It's a trade-off in my mind between how you can explain it and how accurate it can get.
It's hard to see in the light. I think that's all the questions for now. Mohammad, thank you very much.
All right, thank you so much. Thank you.